Okay, so in this video we're going to use a couple of substitutions to solve integrals of the same form. My second example is going to be a little bit more complicated than this one. The idea is that they both all have this general form. I'm going to write up here. This is almost the basic one where we have 1 over x squared plus 1 is the antiderivative of this function is tan inverse or arctangent of x. Right, so this looks pretty similar to that one. Of course, I have a 2x squared, what bothers me. So all we need to do is look at this, like I want to do a little mini u substitution, right? I want to do a u substitution. It's not a big one, but this makes things more cleaner. Substitution, probably didn't spell that right. Where I want this 2x squared to become a u squared. So I want exactly that. I want to write the u squared, I want it to be the 2x squared. Right? So what this means is that really my u is the square root of 2x, correct? I took the square root of each term. Here we're not going to bother about the absolute values of these. I'm going to assume that the u and x are positive if you want, and keep it like this. So now, so pretty simple now, this tells us that the du is really root of 2 of dx. And like I said, I like to solve for the part that is here. I only have the dx in my original integral, so I'm going to solve for dx. So the dx is 1 over root 2 du, right? So that's the mini u substitution that is needed for this integral. So if I'm going to solve it, then this becomes, I have the integral of 1 over this part is u, so I put a u squared, right, plus 1. And the dx, I probably changed colors, but my dx over here that I had up here is 1 over root 2 du. So I put the du over here, and I can put the 1 over root 2 all the way to the front, if we can take it all the way outside. That's a constant, so it can go outside of the integral. So this is all I have to do. And now it has the form to apply the formula from up here. Instead of a u, I have an x, but this is the same. So I have the 1 over root 2 is going to be tan inverse of u plus a constant. And I should not leave my answers in terms of u, so I go back to who is my u, so it's the tan inverse of the root 2 of x plus a constant. Okay, so that would be my answer for this integral. So my second example in this video is going to be the same idea, but a little bit more complicated. So my denominator now is still have like x squared plus something, but it has more terms. It looks a bit more complicated. So I'm still going to be thinking that I'm going to be using this basic antiderivative rule. Sorry, I wrote it backwards. The antiderivative of 1 over 1 plus x squared. Oh, sorry, and I wrote it backwards. Usually we write x squared plus 1. Is just the tangent inverse of x plus a constant. But now I have a few terms in here, so what am I going to do? So here it's going to get a little bit complicated, because what I'm going to try to do is, it's not that hard, but what I want to try to do is, I have these two terms look like the first two terms of a binomial that I can complete to have a perfect square. So I'm going to write, sorry, I can always do that, right? So, but in particular here, I can have like x squared plus 6x. If I want to have a binomial squared, I needed to have a 9, right? So these three terms together become x plus 3 quantity squared, correct? Now I had a 25 up here, and that 25 is now, part of that 25 is taken in that 9, so I can think of like I broke it up like a 9 and a 16. Okay, so this is one way to write it. Another way to write it is to add and subtract the 9 after you have that, so the 25. Subtract the 9, you get a 16. Then I'm going to leave it like that. Those two guys together become that 25 that's up here. Okay? So how does that help me? Well, that helps me because now I'm going to have dx, and I have x plus 3 quantity squared plus 16. Now it looks a little bit better. Now this is kind of what I want, is getting closer to what I have over here, right? I have a quantity squared. I feel like I'm going to have 1 over u squared plus 16, where my u is x plus 3, correct? So I'm on the right track, but to use this rule, I need to have a 1 there, not a 16. So there's one more thing I need to do. So this is going to be wrong, so let me cross this, erase this, but we're on the right track. So what I need to do is one more step where I'm going to write this like, I'm going to factor a 16 from, this 16 here, I want to make it a 1. So how do I make it a 1? I'm going to factor it out. So I'm going to have the integral of 1 over 16 of dx over x plus 3 quantity squared plus 1, right? Now this is not correct because if I distribute this 16, this term is not, this doesn't give me what I had before. This one does, but the first term, I don't have it. So how do I fix that? Well, I fix that by, I'm going to multiply by 16, so I divide by 16. Okay? So again, if you multiply this times this first term, the 16 is going to cancel. It's in the denominator, so it's going to cancel. And 16 times that guy, you get this term that I had. So this is algebraically correct. Okay. And not only that, but because the numbers are working out pretty nicely, I can write this like, I can take the 1 over 16 outside, and I can write the dx, and then write the denominator like x plus 3 over 4 quantity squared, right? Because the 16 is the root of, sorry, it's 4 squared. And there you go. Now I have clearly the correct form for this u substitution, which is really what all I have to do, right? So now I have it in the right form, and I can say, okay, great. Now all I have to do is say, what if I make my u to be x plus 3 over 4? Then it's pretty simple. The du becomes 1/4 of dx because the 4 is a constant. So really, my dx is 4 times du. Okay? So when you plug it in over here, I want to do my u substitution back in. And now my integral here becomes, so this becomes 1/16 of an integral of, I'm going to write 1 over 4, I have a du, so let me put the du here. And I'm going to have the 1 over 4, and then I have, sorry, this is wrong. I don't have a 1 over 4, I have a 4 du. It's in the numerator, right? My dx is 4 du. Okay? And in the bottom, I have u squared plus 1. And now I can just apply the basic integration rule from the top right corner. So the 4/16 cancels to 1/16, sorry, 1 over 4. And I'm going to have tan inverse of u plus a constant. And I'm almost there. So now go back to your x's. 1/4 of tan inverse of x plus 3 over 4 plus a constant. So there you go. So it's the same rule as before, but I had to work a little bit more on it to make it look like I can apply this rule and then use a u substitution to make it work.